I thank Canon Automation for giving the opportunity to me and Schaefer to present our application of panel unit. So my name is Mitun Chidamparam. I'm a software developer at Schaefer. I'm currently there for more than 2 years. My daily routine or my part in the company is I'm in charge of all the products with CAN in Schaefer. So first of all, a short overview about what Schaefer is. So Schaefer is an international company. We have operations all around the world, at least the major part of the world. So Europe, North America, and Asia. We have around 250 employees. The products what we offer in Schaefer, or we offer complete systems in the sense that for the core fixtures, COP panels, hall stations, and position indicators, we also offer individual components like push buttons, displays, acoustic devices, communication devices, access controls, and infotainment systems. Our main specialty is in our push button series. We have varied varieties of them based on the requirements. One of the reasons why we have to use CANopen is that for all of our components like the displays, the push buttons, we need intercompatibility in the sense the wiring should be easier, and at the end the customer can plug in our whole fixture into the system and they will be able to operate it. So CAN is really important for our company. Just a few references. Our products have been installed in some high-rise buildings and important buildings all around the world. If you're interested, you could take a look into it, or you could visit our website. So now let's go back to CAN. So here are a few of the main CAN components, what we use at Schaefer. The green PCBs, what you see on the left side, are our CAN IO modules, which are placed either in the core or in the floors to control, or they connected to the switches or the push buttons or displays or keys, depending on the customer. We also have TFTs with integrated CAN functionality. So they have connectivity with the CAN bus with the black connector here, and we also have possibility of connection to some IO modules like switches and things. Also, there's some output for audio. And for the TFTs, normally the node IDs can be set via our configuration software or through the bus. It holds true also for the small CAN nodes. Here, the node ID is set using dip switches, as you could see. And the configuration here is set with removable EEPROM, which is a small green PCB which you see on the top. This is quite important because these CAN modules could stay in the elevator for many, many years. And maybe if there is some issue where some of the IO modules stop working, then the customer could just buy a new CAN module from us, and even though he doesn't know what has been configured at this particular installation, he could take out the old EEPROM from the old CAN module and plug it into the new one, and he could have intercompatibility. All of our CAN devices have status LEDs, green and red LEDs based on the CiA 303 recommendation to show the status of the CAN nodes or the TFT. This is for the customer or the lift installation person to know what is the status of the CAN node. Are they connected to the bus, or are there some errors and things like this? And during normal operation, there's a steady green light blinking, and for example, if the CAN node doesn't find a heartbeat, then the green light is the green light and the red light are blinking after one another. And for example, if there is a CAN bus found, so there's a heartbeat found from the lift controller, but the CAN nodes are not being set into operational mode, then the green light is blinking at a certain interval. You could find this based on this recommendation CiA 303. So let's go further. I'll show you how our components are connected to the bus. There are two main kind of wiring technologies what we use. So one is where we use kind of a ring wiring system. So this four cables, so the blue and white are the CAN high and CAN lows, and red and black are plus and minus, so the power supply. These cables run as a wire from one lift through the whole shaft or through the whole floors, and from our CAN nodes we use this Vago connector where we just directly plug it into the main bus wire. This is also being used, and we also use a different system where we have a lot of interchanging length of cables, where we plug based on the distances to our floor panels or displays or indicators and further. Inside the car, this is the kind of wiring scheme what we do. So it could be that there's no CAN display in that sense. Then we use the I/O pins to connect to a display which can support CAN with our CAN node. We also connect the switches directly from the CAN node to the bus. And normally in the car panel, we also include a terminator resistor. As you know, in CAN bus, we need to have 120 ohms at each ends, and normally the car panel is the end of the node, so there is a terminator resistor present. And in this case, the TFT has an inbuilt terminator resistor, so this jumper is turned on. Here is the wiring scheme that's being done for the floors. So here you can see there is a lift controller, and there's a wire which is going down through for each of our floor panels. And here we use basically one big cable, and based on different length, we can plug and play our our wires. In this case, it's a group lift system where we have 3 lift controllers which are controlling the whole lift system. There are many ways of implementing it, but in this case, there are 3 lift controllers, so we need 3 floor wires which are going to each floor, and they're connecting to our CAN nodes or TFTs. So let's go on to the basic definition, what is being used in our products. Each of our product have this objects defined so that someone who's doing some lift maintenance can get to know what kind of product it is and how they can go further. So we always have a manufacturer device name, so that's the name of our product. So for example, it's CN16F, so that's a CAN node with 16 IOs. F means it's really it's not thick. We also define the hardware version of it. A software version is also available. And then we have the identity object to identify what kind of object it is. The vendor ID is defined by CiA, and Schaefer it is has been given as the hexadecimal 13B. We have a internal product code of Schaefer, a revision number, and a serial number. Each node which is connected to the bus, as said earlier, we have maximum of 127 modules which are possible to be connected to the CAN bus, at least one CAN bus. And for that, we need to have some unique identifications. And so we could define the node ID based on the DIPS switches or software. So using the bus itself, using STO protocol, we could change the node ID. It's similar to the baud rate. Normally, we use for the car panels a baud rate of 250 kilobits, and for the floor panels 125. But it depends on the lift controller; it could change. CiA also recommends a set of node IDs which are to be used for the lift controllers. It goes from 1 to 8. And for the core panel modules, it goes from 16 to 20. So the panel modules also includes a display, a TFT display and things like that. And for the floor IO panels, it goes from 21 to 84. We need more node IDs for the floor IO panels because so each floor maybe has more than one module. And the core panels, there have been 4 IDs defined because there could be maximum of 4 doors in a core panel. So each door has one module, let's assume. But more or less, we are flexible with it based on the manufacturer requirements. It could always be changed. So let's go to the virtual devices. As has been told earlier, by using virtual devices, we could configure or we could know the status of each of the panel, so the CAN nodes which are connected to the bus. Let me use some short examples. So for the input panel, CiA, so this application profile of Lift has defined 0 times 6010, and for the output panel has 6011. That's where the mapping of the input objects and the output objects can be found. The IO pins can be configured by the virtual device mapping. For example, one of the smallest nodes what we have, the CN08, so it has 8 IO pins. So there we could define 8, so we could connect, for example, 8 switches or buttons, or it could be connected to a display with 8 inputs. Yeah, so this Lift profile also has 0 times 6220, where we could enable or disable the input pins. And when we use the SDO protocol, for example, to read what has been configured in this particular CAN node, there is a defined EDS file. And based on this EDS file, the Lift controller or the tool which is used to scan the bus can know what objects it needs to ask in the CAN node. And when it scans the object 6100, it knows that, okay, it's a CN08F, which has 8 IO pins. So then there can be 8 virtual inputs. And I have shown here an example where the virtual input 1 has been configured as a core call button. And when it reads it, it would get this message. So there it means that 05 is defined by this Lift application profile as a core call, and 01 is to show which Lift is it connected to, and the next 01 is to show the which floor, and then you have 11 to show the destination door and the source door, and 00 is to show the status. By virtual input, this status bit is quite important for technicians who are in the field for debugging. This is needed because by using Lift CAN controller or the bus, they can read the status of each bit. So for example, if this virtual input is high, then here we would get a status message of 01. So let's go on to the next slide of the output panels. So similar to the input panels, the 0 times 6220 can be used to enable or disable the outputs. So I have a small typo here. It should be called virtual output because it's 6200. Anyway, let's go further. When this is being read over the bus, then you could see it as a similar description to the input panel, where it's 05 to show the code acknowledge, and 01 and white and further. And here at the end, we have the 00, which is the status byte. This is to show that this output is not high. So the input and the output settings can be controlled. This is the reason behind this is that by design, we have all our pins, the input and the output pins pinned to the same pin of the microcontroller. So that means that each pin of the IO pins can be used as either an input or as an output. And this is being done based on a pulsating system where even though this pin is high, so that means that the LED of the button is high, even if the customer is going to press this button, there is going to be a message sent to the lift controller to show, hey, this button has been pressed again. The use case behind this is that in some special cases where it's a fireman elevator, then the button always has to be pressed, and also the button always has to glow when it's being pressed, because to show to the end user that, hey, the lift controller acknowledges your press and keep pressing it for 5 seconds, or also for alarm or things like this. This can be set for our CAN nodes in these objects. So now let's go on to our virtual device communication. The lift controller, as I said earlier, or has also been said earlier, is defined with node IDs from 1 to 8. And all of our CAN nodes are always looking for a heartbeat from the lift controller, and the heartbeat from the lift controller has this particular address, so which is determined by 0 times 700 plus the hex value of the node ID of the lift controller. So if it's 1, then it's 0 times 701, and it sends a message always 05 to show, hey, it is active. When we don't get this heartbeat, then all of our CAN nodes and our TFTs go into out of order situation. And if there are some indicator present, so the TFTs have an indicator present, then we show the out of order symbol. Based on this, the user can know what is the status of the system, and they could call a technician, for example. So here's an example to show you how the startup of the network works. This was also briefly covered by Mr. Roy Schneider previously. When the lift controller is connected to the bus, and it normally sends a reset communication, and all of our connected nodes also do a reset, and they show their existence to the lift controller. And once they show their existence, they automatically go into a pre-operational mode when they see an heartbeat, and then they're waiting for an empty start remote node message from the lift controller. Once they receive their start remote node from the lift controller, then the CAN nodes go into operational, but simultaneously they also send what the IOs or the virtual devices has been configured in this particular CAN node. Based on this, the CAN controller can save it in their system to know what each node has been configured. Here is a small example where the NMT start remote node is sent from the lift controller, and then the CAN node automatically goes into operational mode. So it's node 16, and then it says, hey, my pin 1 has been configured as 0521 blah blah, and that actually means it's a core call at floor 33 for floor A. So here is an example message for core or floor panel. Here it's for floor indication message. All the PDO messages here have a size of 6 bytes. So the first byte shows the basic function, the second byte to show sub function, third byte to show the lift, the fourth byte to the floor, fifth byte for the door, and the sixth byte to show the function data. So here it is 40. So defining this lift profile, 40 is basic function floor indication, and the sub function 04 determines which floor it is. So the displays need to show floor 4. And this special case with the basic function 40 where the status bytes are not being used. Then let me show an example of how a button press is being sent to the lift controller. So when a button is pressed and this virtual device is configured as a core call floor 1, then it's being configured as basic function 05, and this, it sends this PDO message. So basically 0501. And for the with its particular ID, so the ID for this particular node would be hex 490 plus hex 16, which would be sent to the lift controller. And when the lift controller says, okay, the lift can move to this particular floor, then it sends back an acknowledge message. And if the same IOPen is configured as input and output, then this button would also be turned on, but there is no message sent back to tell the lift controller that it turned on the virtual output. So there's no PDO for that. Basically, only when there's an input, the lift controller sends a PDO. For outputs, there's no PDO sent. So here I'm going to show you the basic functions which are defined by the lift can profile for call functions. Call is different from input, where call actually means that it is being used as an input and also as an output. So when the CAN node sends this car call, for example, then it means it also has an input virtual device and also has an output virtual device. But that's not always the case. It could be. For car call, the basic function defined is 0 times 5. There can be up to 254 flows based on this lift profile. Here it is, we always need to look into subfunction to know what floor it is connected to. So it's 03, that means it's the third floor. Then 01 to show which lift it is connected to. So 1 is lift 1, and 11 to show the source and the destination door. So the right bit is the source door, and left bit is the destination door. And 01 to show the status. So if it is being pressed, then it sends a 01. It's similar for the hall calls. Hall calls are used in the floor panels. There we have the basic function of 02, and the subfunctions can be up, down, or up and down both together, or directional or unidirectional. I think there are 4 subfunctions defined, or 5. So here is the subfunction is 01, so that means it's up button, and since the status byte is 01, so that means it sends to the lift controller that this up button has been pressed. There are also some special functions defined to send signals to the lift controller where, for example, there's a fire and they need to send a signal, or there is a communication device, since there's an emergency and they need to use some communication device, and this communication can be controlled based on green or yellow pictograms, which are defined by the EN 8170 norm, which shows you how the emergency communication should be done. And the basic function for the special function is 0E, and there are 35 predefined signals, and based on the manufacturer, we could also define more. And this should always be communicated between the lift controller manufacturer and the car IO panel manufacturers and the end user, so what system he wants to use. So now let's go to the display indication. For a normal display, we always use the basic function 0 times 40, where each floor is sent. So so floor 1 is 1, and the subfunction is the floor value. So here we have 03 as subfunction, so that means it's third floor, and it can go up to 254. But always we cannot use this case because there are a lot of dot matrix displays which don't support CAN, so we need to connect them to our CAN nodes. For these situations with the lift controller manufacturers, we have determined some coding mechanism. In the sense, our CAN nodes send out a coding scheme that our dot matrix displays can recognize. So for binary coding, we use the basic function 0 times 80, and for gray coding, it's 0 times 81. And then there are 5 sub functions for each of this binary coding or gray coding. There can also be 7 segment displays, and for that, the basic function is 0 times 83. And for arrow indication, there can be two kinds of arrow. So there can be arrow in the core, and there can be arrow in the floors. For the floor arrows, the basic function is 0 times 41, and for the core panel, the arrow indication is 0 times 42. And each of the IO panels or the TFD should be configured based on its location. Is it in the core or is it in the floor? So now let's go to the special indication. So a lot of people confuse the special indication to the special indication call, which we saw previously. They are quite different. Maybe the names look similar, but they really have different functionality. But here it's just an output to show what is the status of the elevator or what has been sent from the lift controller. There are some 30 predefined signals already there. So these are the sub functions. Based on the requirement, more can be defined. Here's a small example where the basic function is 43, so special indication. So 03 is the third one where it's defined as overload. One more thing to note is that many lift control manufacturers and users determine the priority of the special signals based on their sub function, but it's not really defined so, but it has been written that way that for example, overload has a higher priority than another special signal. Special signals are usually sent with FF. So FF means all floors and all doors. This is because if the lift is overloaded, each floor panel and all the core panels are overloaded and the lift can't move. So normal use case is that it's being always sent with FF for floors and doors. Some of the displays can also have a next stop indication where all the floor buttons have been pressed, but the lift controller can determine the priority which is going to be the next floor where the lift car is going to stop, and that basic function is 0 times 4c, and the sub function similar to the floor information shows which floor it is going to be. So we also need auditory indication because the floor announcement should be announced for each floor, and or some special signals should be set. For floor announcement, it is 0 times 47, and the sub function shows which floor it is. For floor announcement, similar to the floor indication, where we have binary coding and gray coding, there are also some manufacturer-defined basic functions. I didn't include it here, but if you have further questions, you could ask us. Similar to the floor indication, the status message is ignored. So if it's 00, it means there is no floor. If it's 01, then it, or 02, it doesn't matter. So the actual status, which floor the current core is in, is set by the sub function. So the status bytes is ignored by the floor indication and the floor announcement. For the vocal messages, so there are the special signals. So we have 0 times 48. So there are 22 predefined signals here. And here, for example, basic sub function 12 is wait for the rescue service. Normally, here also the status bytes are ignored, but it has not been defined like that in the lift application profile. So one more interesting thing is the way the indication of our buttons are being done. For example, if the car is getting closer to a floor and this floor button can start blinking at different frequencies to show to the user, hey, he's going to reach the destination floor. Or if there is a text on the display, then it could move at different rates, or the volume can be adjusted, or if there are RGB LEDs, then their color can be changed. This is being done by manipulating the status byte. So basically, the status byte, as I said, is here. So the last byte of the PDO message. And in the Lift application profile, it has been determined. So it has been defined here, and based on this, or it's not necessary that all of this has to be supported, but based on the application or based on the device, only some of the functions are supported. Let's go further. In all of the displays, normally we also have indication to show what is the time and date. One of the funny stories that in Frankfurt Airport in Germany, at Schaefer, we had installed a lot of displays without CANopen, and the problem was all of our customers are always complaining that the time doesn't match up. Since in CAN we are using a bus system, all the displays or all the indicators can be synchronized at the same time, and most of the CANopen lift control manufacturers use the standard CAN identifier as 100 to send the time of the day, the current time, and this is being implemented in most of our displays. And here there are, till now there has been no reclamations. That's it for my presentation. To give a short overview what we talked about, in Schaefer we have components which are compatible with this Lift CANopen profile. The goal is to ensure plug and play compatibility, because when the customer orders things, so he's going to order the lift controller at a particular date to the lift controller manufacturer, and he's going to order the car fixtures with us, with Schaefer. And both of these components are put together in the installation site, and by the time it goes to the installation site, all of the things should be cleared up. The configuration should be passing to the lift controller. So that's what we try to ensure, that in the end stage we just have to plug it in and it's going to work out of the box without the need of any technician or any system integrator. To ensure this kind of compatibility, each of the CAN nodes or the TFTs should have or should know what baud rate the system is going to work in. Or we could also use the recommendation from CiA. It shows how you could implement the auto baud functionality. So even this human error where we could set a wrong baud rate is minimized. Each node should be assigned a unique node ID, so there are no conflicts between different nodes. And if the recommendation from the profile is being used, then this issue could be minimized. The virtual device configuration can be configured based on the user need, because a button is a simple button, but what this button is going to do, this function is really configurable based on the Lift application profile or based on the customer requirements. And this customization is what makes this a really unique process. If you have any questions, please go ahead, and thank you a lot for your time.